Tonight, we're going to sit with one of the strangest facts ever discovered about the universe, and we're going to take our time with it. The fact is this: almost everything that exists is made of something no one has ever seen. Not seen through a telescope, not caught in a laboratory, not photographed, not weighed in the hand, not identified, not named in any deep sense at all. And yet it is here, all around you, right now, holding the stars in their places, keeping the galaxies from flying apart, shaping the entire architecture of the cosmos from behind a curtain it has never once stepped out from. We call it dark matter. And the honest truth is that the name is mostly a way of admitting how little we know. By the end of tonight, you'll understand why scientists are so completely certain that this invisible thing is real, even though every single attempt to catch it directly has come back empty-handed. Year after year, decade after decade. You'll understand how we can be confident about the existence of something we have never detected, and you'll understand the quiet, unsettling possibility lurking underneath all of it. That maybe, just maybe, we've misunderstood something far more basic than we think. We won't rush to that. We'll arrive there slowly, the way you arrive at the edge of sleep, one soft step at a time. If you find this kind of slow wandering through big ideas restful, or if it helps quiet the noise of the day, it would mean a great deal if you gently tapped like or subscribed before you drift off. It's a small thing, and it helps these quiet hours find the other people who are lying awake somewhere, looking for the same kind of calm. That's all. No more of that tonight. Now let's begin. Let's start with where this story actually begins, which is not with anything exotic or invisible at all. It begins with something you've done 1,000 times without thinking about it. It begins with looking up. Picture yourself outside on a clear night, far from any city. Somewhere the air is cold and still and the sky has opened all the way up. You tilt your head back, and there they are. Stars, more than you can count, scattered across the black like grains of sugar spilled on a dark floor. And the first thing your mind does, almost automatically, is to read that scene as mostly empty. Little points of light, and between them, nothing. A vast, patient blackness that seems to be the absence of things rather than the presence of them. That reading feels obvious. It feels like simple common sense. The stuff of the universe is the bright stuff, and the dark is just the gap where the stuff isn't. For almost all of human history, that was the assumption nobody even bothered to question because there was no reason to. Our eyes evolved to do one job extraordinarily well, which is to catch light. Light bouncing off a predator in the grass. Light glinting off water. Light from the sun and the moon and the campfire. Everything our ancestors needed to survive announced itself by interacting with light, and so we came to feel, deep in our bones, that to be real is to be visible. If something is there, you should be able to see it, or at the very least shine a lamp on it and watch it appear. That instinct is so deeply wired into us that we rarely notice it's an instinct at all. We just call it reality. And for a long time, the science of the heavens leaned on that same instinct. To measure the universe, you counted the light. You pointed your telescope at a galaxy, you measured how brightly it glowed, and from that brightness you could estimate how many stars it held, and from the number of stars you could estimate how much matter was there. More light, more stuff. Less light, less stuff. It was a clean, sensible bookkeeping, and it worked beautifully right up until the moment it didn't. Because the universe, as it turns out, keeps two sets of books. And it took a strange, prickly, brilliant man to notice that the numbers didn't add up. His name was Fritz Zwicky, and to understand how the discovery of dark matter began, it helps to spend a moment with him, because the story is in many ways the story of a man being right at a time when nobody was ready to listen. Zwicky was a Swiss-born astronomer working in California in the 1930s, and by all accounts he was difficult, famously, gloriously difficult, the kind of scientist who insulted his colleagues and trusted his own measurements over the comfort of the crowd. But he had an eye for things other people overlooked, and in the early 1930s he turned that eye toward a cluster of galaxies far out in the constellation we know as Coma Berenices. Now, to picture what Zwicky was looking at, you need to scale up your imagination slowly in stages because this is the kind of size that doesn't fit into a single thought. Start with a single star like our sun. Already that's a furnace so large you could pour 1,000,000 Earths into it. Now gather a few 100 billion of those stars together, bind them with gravity, and let them turn slowly in a great wheel of light. That's a galaxy. And now take not one galaxy, but 1,000 of them, all swarming together in the same region of space. orbiting a shared center of gravity like bees around an invisible hive. That is a galaxy cluster. The Coma cluster is one of these, a great congregation of more than 1,000 galaxies, sitting some 300 million light-years away from where you are right now. Zwicky wanted to weigh it, and he had a clever way to do it, one that didn't depend on counting the light at all. He measured how fast the individual galaxies were moving inside the cluster, how quickly they were darting around within that great swarm. And here's the elegant idea behind his method, the one you can feel in your own body without any equations. Imagine you're standing at a playground watching a merry-go-round spinning fast, and there are children clinging to the bars at the edge. If that merry-go-round is spinning quickly and the children are still holding on, you can immediately conclude something about the strength of their grip. A weak grip and they'd be flung off into the dirt. The fact that they stay means the force holding them in must be strong enough to match how fast they're moving. The faster the spin, the stronger the grip has to be. You don't need to measure their hands. The speed tells you. Gravity works as that grip for a galaxy cluster. The galaxies inside are racing around, and the only thing keeping them from scattering off into the dark is the collective gravity of everything in the cluster. And gravity, of course, comes from mass. So if you measure how fast the galaxies are moving, you can work backward and calculate how much mass the cluster must contain in order to hold those fast galaxies in. It's the cosmic version of looking at the speed of the children on the merry-go-round and deducing the strength of the grip that must be keeping them aboard. So Zwicky measured the speeds. And then, separately, he did the old-fashioned thing too. He added up the light, estimated the number of galaxies and the stars within them, and calculated how much mass the cluster appeared to contain based on everything that was actually glowing. And the two numbers did not match. They didn't miss by a little. They missed by an enormous, almost embarrassing margin. The galaxies in the Coma cluster were moving so fast that the cluster should have torn itself apart long ago. The galaxies flinging off into deep space like children losing their grip on a merry-go-round spinning far too quickly. The visible matter, all those glowing stars, all that light, came nowhere close to providing enough gravity to hold the swarm together. By Zwicky's reckoning, the cluster needed many times more mass than anything he could see in order to make sense. Something else had to be there, something with a great deal of mass, pulling everything inward, and yet giving off no light at all. Zwicky had a name for it in his native German. He called it Dunkel Materie, dark matter, and take a moment to appreciate how restrained that name actually is, because there's a temptation to hear it as something spooky or mystical, and it really isn't meant to be. He wasn't claiming to have found ghosts or some shadow dimension. He was simply stating, as plainly as a person can, the two things he was sure of. It is matter because it has mass and it pulls with gravity. And it is dark because it gives off no light. Matter that is dark. Dark matter. The name is almost a shrug. It's a way of pointing at a hole in the books and saying, here, something belongs here, and we don't know what it is. And here is the part of the story that I find quietly remarkable, the first of our open threads tonight, the one I want you to keep in the back of your mind as we go. Zwicky made this measurement in 1933. The bones of the dark matter problem were laid bare almost a century ago, and the world's astronomers, by and large, did not panic, did not rush to investigate, did not declare an emergency in the foundations of physics. They mostly shrugged it off. For roughly 40 years, this enormous, glaring discrepancy sat in the literature like a strange stone nobody wanted to pick up. The idea that most of the universe might be invisible was simply too big, too inconvenient, too easy to explain away with the hope that the measurements would eventually tidy themselves up. Maybe Zwicky had the distance wrong. Maybe there was gas out there that hadn't been counted. Maybe the man was just difficult, and difficult men make mistakes. Hold on to that. The fact that a discovery this profound could sit in plain sight, ignored, for nearly half a lifetime. Because the question of why the scientific world finally couldn't ignore it any longer, and who forced the issue, is where this story turns, and we'll come to that soon. For now, let's stay with the strangeness of what Zwicky had stumbled into, because it deserves to be felt slowly. He had found, in essence, that the universe weighs more than it looks. And that's such a quiet sentence for such a staggering idea. We are used to the opposite kind of surprise. A box that's lighter than it looks, a suitcase that turns out to be empty. But the cosmos was heavier than it looked, and not by a comfortable, explainable amount. It was heavier in a way that suggested the part we can see, the glowing part, the part our eyes and telescopes were built to detect, was not the main event at all. It was a thin, bright skin stretched over something vast and dark and silent. Let yourself sit with the reversal there. Everything you have ever looked at in the night sky, every star, every planet, every smear of a distant galaxy, every comet and every cloud of glowing gas, all of it, the entire glowing inventory of the cosmos, might be the minority. The footnote, the decoration, and the actual substance of the universe, the bulk of what's truly out there, might be something that has never once announced itself to a single human eye. It's a little like walking into a grand old house at night, lit only by candles. You see the candle flames here and there, marking out the rooms. And it's natural to think of the house as those points of light. But the candles aren't the house. The house is the walls and the floors and the great dark beams holding up the roof, all the structure you can't see in the dark, the architecture that the candles are merely sitting inside. The flames feel like the important thing because they're the thing you can see, but they're just resting in a structure that was there long before they were lit, and that would still be there if every flame went out. Dark matter, it would turn out, is something like that structure. The stars are the candles, and we had spent all of human history mistaking the candles for the house. Now, I want to be careful here because it would be easy to let this slide into something vague and dreamlike, and the whole point is that it isn't vague at all. This isn't poetry dressed up as science. These are measurements. Hard, stubborn, repeatable measurements that keep insisting on the same uncomfortable answer no matter who takes them or how. And the reason the discovery eventually became impossible to ignore is that the evidence stopped coming from one prickly man and one distant cluster, and started coming from everywhere by completely different methods, all pointing the same way. But that fuller picture took decades to arrive. In Zwicky's own time, the tools simply weren't sharp enough to force the issue. Telescopes were good, but not good enough to settle the argument. The measurements had wide margins of error, plenty of room for a skeptic to wave the problem away. And so the strange stone sat there, in the cluster called Coma, 300 million light-years off, quietly insisting that the universe was full of something we couldn't see, while the rest of astronomy looked the other way and got on with the comfortable business of cataloging the light. So let's leave the great galaxy clusters for now, with their thousand swarming galaxies and their missing weight, and let's come closer to home. Let's come down to the scale of a single galaxy because that's where the second crack appeared, and this time the crack would be too clean and too widespread to ignore. To get there, though, you first need to understand a simple piece of how gravity arranges things in orbit, and the best teacher for that is right in our own backyard. Our own solar system. You've almost certainly absorbed the basic picture at some point. The sun in the middle and the planets going around it in their rings, Mercury closest, then Venus, then Earth, and on out to the cold and distant giants. But there's a detail in that picture that doesn't get talked about much, and it turns out to be the key to everything. The planets don't all travel at the same speed. The closer a planet is to the sun, the faster it moves. The farther out it is, the slower it goes. And this isn't a coincidence or a quirk. It's a direct, unavoidable consequence of how gravity works. Think of it this way. Gravity from the sun is like a tether, and it gets weaker the farther out you go. Close to the sun, the tether is taut and strong, so a planet has to whip around very fast to keep from being pulled straight in. The speed is what holds it out against that strong inward tug. Far from the sun, the tether is slack and weak, so a planet only needs to dawdle along slowly to stay in its orbit. Mercury, sitting close, races around the sun in just 88 days, moving at a blistering pace. Neptune, far out in the cold, takes 165 years to make a single lap, creeping along its enormous orbit. The pattern is rock solid. Inner things move fast, outer things move slow, and the fall-off in speed follows a precise mathematical curve that astronomers had understood since the days of Kepler and Newton centuries ago. So here's the natural expectation. If you have a galaxy, a great spinning wheel with most of its bright mass concentrated toward the center, where the stars are packed densely and a giant black hole often anchors the core, then the stars in that galaxy ought to behave like the planets in a solar system. The stars near the center, close to all that concentrated mass, should orbit quickly, and the stars way out on the lonely fringes of the galaxy, far from the central bulge, should orbit slowly, dawdling along just like Neptune, because the gravitational tether out there should be weak and slack. Plot the orbital speed of stars against their distance from the center, and you should see a curve that rises, peaks, and then gently falls away as you move outward. That falling tail is the signature of gravity behaving the way it's supposed to. Out at the edge, where there's hardly any visible matter and the central mass is far away, the stars should be slowing down. That was the prediction. That was what every working astronomer expected to see. And it was so obviously correct, so firmly grounded in physics that had worked perfectly for the planets in our own backyard, that for a long time nobody thought to look very carefully. Why would you? You don't carefully recheck whether water is wet. But in the 1960s and into the 1970s, the tools finally became sharp enough to actually measure those outer stars properly, to clock the speed of the faint material spinning around the distant edges of galaxies. And the person who did this work more carefully and more persistently than anyone, the person who would finally drag dark matter out of the footnotes and into the center of the conversation, was an astronomer named Vera Rubin, working with her colleague Kent Ford. Vera Rubin's path to this work is worth pausing on, because she was operating in a field that, in the middle of the 20th century, did not exactly roll out a welcome mat for women. There were observatories she was not permitted to use. There were rooms she was not invited into. And rather than fight every one of those battles head-on, she made a quiet, shrewd decision early in her career. She chose to work on problems that were so unglamorous, so seemingly settled, that nobody would bother to compete with her or push her aside. Galaxy rotation was exactly that kind of problem. It looked boring. It looked done. Everyone already knew what the answer would be. And so she was left alone to do it properly, which is precisely how some of the most important discoveries get made, by someone patient enough to carefully measure the thing everyone else assumed they already understood. So picture her, in the dark of the observatory, pointing her instrument at the great spiral of the Andromeda Galaxy, our nearest large neighbor, 2.5 million light-years away. Andromeda is the closest big spiral to us, a vast pinwheel of a few hundred billion stars, and from our vantage point it's tilted at an angle so that one side of the disk is rotating toward us and the other side is rotating away. And this is the lovely thing, that motion leaves a fingerprint in the light itself. You already know this fingerprint from everyday life, even if you've never named it. It's the reason an ambulance siren sounds higher in pitch as it races toward you and then drops to a lower pitch the instant it passes and starts speeding away. The sound waves get squeezed together as the source approaches, raising the pitch, and stretched apart as it recedes, lowering it. Light does exactly the same thing. When a star is moving toward you, its light gets very slightly squeezed toward the blue end of the spectrum. When it's moving away, the light gets stretched toward the red. By measuring that tiny shift in the color of the light coming from different parts of Andromeda, Rubin and Ford could read off with real precision how fast each region of the galaxy was spinning. The side coming toward us shifted blue. The side going away shifted red. And the amount of the shift told her the speed. So she worked her way outward from the bright center of Andromeda, region by region, measuring the rotation speed at each distance, fully expecting to watch those speeds climb to a peak and then begin their graceful decline. The falling curve, the signature of gravity behaving itself, the same pattern that Mercury and Neptune trace out so faithfully in our own sky. The speeds climbed, and then they didn't fall. Out past the bright central bulge, out where the visible stars thinned to almost nothing, out where there was hardly any glowing matter left at all and the rotation speed should have been dropping away towards zero. The stars and gas were still moving just as fast as the material much closer in. The curve didn't peak and decline. It rose and then went flat, stretching out level as far as she could measure, like a road that climbs a hill and then refuses to come back down, running straight out to the horizon. The outermost material in Andromeda was orbiting at roughly the same brisk speed as material far closer to the core, and by every rule of gravity that had worked perfectly for centuries, that should have been impossible. Sit with what that flatness actually means because it's the whole game. For those distant stars to be moving that fast and yet remain bound to the galaxy. For them to stay in orbit rather than go flying off into intergalactic space like sparks off a grindstone, there had to be enormous additional gravity holding them in. Far more gravity than the visible stars could possibly account for. And the only source of gravity is mass. So there had to be a tremendous amount of mass out there in the dark fringes of the galaxy, far beyond where the starlight faded out, mass that was tugging on those outer stars and keeping them locked in their fast orbits. Mass that gave off no light. The exact same conclusion Zwicky had reached 40 years earlier, staring at his swarm of distant galaxies. Except now it was showing up in the gentle, ordinary spin of a single nearby galaxy, measured cleanly and carefully, with no easy way to wave it off. And here was the detail that made it impossible to dismiss as a fluke. It wasn't just Andromeda. Rubin and Ford turned their instrument to another galaxy and found the same flat curve. And another, spiral after spiral after spiral, dozens of them, every single one telling the same story. The rotation curves stayed flat when they should have fallen. Galaxy after galaxy was spinning too fast to hold itself together, and yet there they all were, holding together perfectly, billions of years old and entirely intact. There was no longer any way to blame a single bad measurement or one strange cluster. The universe was showing the same anomaly everywhere astronomers cared to look. The pattern was as universal as the law it seemed to be breaking. This is the moment the science genuinely shifted. The strange stone that Zwicky had set down and everyone had stepped around for 40 years was suddenly being picked up and examined from every angle, because Vera Rubin had shown that the missing mass wasn't a quirk of one faraway cluster. It was woven into the fabric of ordinary galaxies, including, by clear implication, our own. The Milky Way you live inside, the galaxy whose faint band you can see arcing across a truly dark sky. It too must be wrapped in this invisible mass, or it too would have flung its outer stars away long ago. And this is the moment to pay off the thread I asked you to hold near the start of tonight. The strange fact that Zwicky's discovery sat ignored for the better part of 40 years before anyone took it seriously. Why? Why does a profound truth get noticed, set down, and stepped around for half a lifetime before the world finally picks it up? It's worth understanding, because it tells you something true about how knowledge actually moves, which is far messier and more human than the tidy version we're usually taught. Part of it was simply the tools. In Zwicky's day, the measurements of those swarming cluster galaxies carried real uncertainty. There was wiggle room, enough that a comfortable mind could tell itself the discrepancy might shrink once the instruments improved. A single startling result on the far edge of what your equipment can measure is always easier to set aside than a clean result you can take 100 times over. Rubin's rotation curves were different in exactly that way. They were close to home, sharp, repeatable, and they showed up in galaxy after galaxy after galaxy, dozens of them all telling the identical story. You can dismiss one strange measurement of one distant cluster. You cannot dismiss the same impossible answer arriving from every spiral galaxy you point your instrument at. The evidence had crossed from anomaly into pattern, and patterns are much harder to look away from. But part of it, too, was human, and it's worth being honest about. Zwicky was abrasive, isolated, quick to insult the very colleagues whose attention he needed. Ideas don't travel well when their messenger has burned the roads. And the idea itself asked for something the field wasn't ready to give. It asked astronomers to accept that most of the universe was invisible, that the light they had built their entire science around was a minority report, that the careful catalogs of glowing things were catalogs of the exception rather than the rule. That's an enormous thing to ask of people, and minds protect themselves against enormous things by finding smaller explanations to reach for first. It's not stupidity or stubbornness. Exactly. It's the ordinary inertia of a settled picture, the very human preference for tidying a small corner over rebuilding the whole house. Science likes to imagine itself as instantly responsive to evidence, but in practice it's run by people, and people need time and repetition, and the slow accumulation of results from many directions before they'll let go of a comfortable world and step into a stranger one. What finally tipped it was not any single dramatic moment but a convergence. Rubin's clean and undeniable curves arriving just as other lines of evidence were maturing, until the missing mass was being reported from so many independent directions at once that the smaller explanations simply ran out of room. And when the field did finally turn, it turned fully. The thing Zwicky had been mocked or ignored for is now textbook cosmology, the foundation of how we understand the structure of everything. There's a quiet justice in that, and also a quiet warning. The next profound truth about the universe may already be sitting somewhere in the literature right now, noticed by someone the rest of us aren't quite ready to hear, waiting its own 40 years. It's a humbling thought to carry, that being right is sometimes not enough, that the truth can be in plain view and still have to wait for the world to grow ready for it. And so a picture began to take shape, a way of imagining what this invisible mass was actually doing. The picture is this: every galaxy is not really the bright spinning disk we see in photographs. That bright disk is just the glowing core sitting at the center of something far larger. Surrounding each galaxy, extending far, far beyond the edge of the visible starlight, there is an enormous, roughly spherical cloud of dark matter. Astronomers call it a halo, though that word can be a little misleading because it isn't a thin ring around the outside. It's a vast three-dimensional sphere of invisible material that the bright galaxy is embedded inside, the way the yolk sits inside the much larger white of an egg, or the way a single firefly might hang glowing at the center of an enormous dark room. The starlight you see is the firefly. The halo is the room, and these halos are not small. The dark matter halo around a galaxy can extend many times farther out than the visible stars, and can contain several times more mass than everything that glows. If you could somehow switch your eyes to see dark matter instead of light, the night sky would transform completely. Those neat, contained pinwheels of light would swell into great bloated spheres, overlapping and crowding the sky, the tidy galaxies you know revealed as just the bright sediment that settled into the center of something vastly larger and heavier and entirely dark. Now, you might reasonably ask the obvious question at this point, the question every skeptic asked and kept asking, because it's a good one and it deserves a real answer. If there's all this extra mass out there, why couldn't it just be ordinary stuff that simply isn't glowing brightly enough for us to see? The universe is full of things that don't shine much. Cold gas, dust, burnt-out stars, dim little failed stars that never got hot enough to ignite, rogue planets drifting alone, black holes. Couldn't the missing mass just be a great quantity of perfectly ordinary, faint, dark, normal matter that we'd been undercounting all along? That would be so much more comfortable. No new physics, no mysterious substance, just a lot of dim, ordinary stuff hiding in the dark. It's the right question to ask, and for a while it was a genuinely open possibility, and astronomers gave it the serious effort it deserved. They went looking for that ordinary dark stuff with great care. They searched for cold gas using radio telescopes because gas, even cold gas, has ways of revealing itself across the radio part of the spectrum. They looked for the faint glow of dust. They devised ingenious methods to hunt for dim, isolated objects, chunks of ordinary matter drifting in the halos of galaxies, by watching for the brief flash of brightening that happens when such an object passes in front of a more distant star and bends its light. They added up everything ordinary they could possibly find or infer. And it wasn't enough. Not nearly. There simply isn't enough ordinary matter, in any form, glowing or dark, to account for the gravity that the galaxies and clusters so clearly demand. But the truly decisive evidence that the missing mass cannot be ordinary stuff, that it has to be something genuinely new, something fundamentally unlike the atoms you and everything around you are built from, that evidence comes from two of the deepest places in all of physics. It comes from the first few minutes after the birth of the universe, and from the faint afterglow of that birth still washing over us today. We're going to get there, and when we do, it closes the door on the comfortable explanation almost completely. Keep that thread in mind. The comfortable answer that it's just ordinary dim matter was tested and it failed. Hold the question of why open, and we'll pay it off when we reach the early universe. But before the very early universe, there's another whole line of evidence I want to walk you through, and it's a beautiful one because it doesn't rely on watching things spin at all. Up to now, every piece of evidence we've discussed has come from motion, galaxies moving too fast in a cluster, stars orbiting too fast at the edge of a spiral. A determined skeptic could still cling to the hope that maybe we just don't fully understand motion and gravity on these enormous scales, that maybe the rules themselves bend out there somehow. So what we'd really want is a completely independent way to weigh a galaxy or a cluster, one that has nothing to do with how fast anything is moving. A way to put the universe on a scale that works on an entirely different principle. And it turns out there is one. It comes from one of the strangest and most beautiful predictions in all of physics, the discovery that gravity can bend light itself. To understand how gravity bends light, you have to let go of an old picture and pick up a stranger, truer one. The old picture, the one most of us carry around, is that gravity is a force, an invisible pull reaching out across space, the way a magnet tugs at a paperclip. That picture works well enough for everyday life. But about a century ago, Albert Einstein gave us a deeper one, and the deeper picture is that gravity isn't really a pull at all. Gravity is the shape of space itself. Here's the image that's usually used, and it's worth slowing down on, because once it clicks it never leaves you. Imagine a large, taut sheet of rubber stretched out flat, like a trampoline. Now set a heavy bowling ball in the middle of it. The sheet sags, dipping down into a bowl-shaped well around the ball. The ball hasn't reached out and grabbed anything. It's simply made a dent, a curve in the surface around it. And now if you roll a small marble across that sheet, the marble doesn't travel in a straight line as it passes near the ball. It curves, following the slope of the dent, falling inward along the bend in the sheet. From a distance, it looks exactly as though the bowling ball is pulling the marble toward it. But really, the ball is just bending the surface and the marble is just following the bend. That, Einstein realized, is what mass does to the universe. Mass bends the space around it. Not a flat rubber sheet, but the full three-dimensional fabric of space, and time woven in with it. And everything that moves through that region, everything follows the curve. The planets aren't really being yanked by an invisible cord from the sun. The sun has put a deep dent in the shape of space, and the planets are simply rolling along the slopes of that dent, around and around, in the straightest paths available to them through a curved landscape. And here is the part that matters for tonight. If mass bends the very shape of space, then it bends the path of everything traveling through that space, including light. Light always takes the most direct route available to it, but if the space it's crossing is curved, then the most direct route is itself a curve. So when a beam of light from some distant object passes near a great concentration of mass, a galaxy or a whole cluster of galaxies, that light gets deflected. Its path bends around the mass the way the marble's path bends around the bowling ball. Einstein predicted this, and it was confirmed during a solar eclipse, when astronomers measured the light of distant stars bending ever so slightly as it grazed past the edge of our own sun. The stars near the eclipsed sun appeared shifted from their true positions, exactly as Einstein's equations said they should. Gravity bends light. It was one of the great triumphs of 20th century physics. Now think about what that gives us. It gives us a scale, because the amount that light bends as it passes a clump of mass depends directly on how much mass is there. A little mass, a gentle bend. A lot of mass, a sharp one. So if you can find light from some distant galaxy that has traveled to us by passing through or near a closer cluster of galaxies, and you can measure how much that light got bent on its way, then you can calculate exactly how much mass the cluster contains, without ever measuring the motion of a single thing inside it. You're weighing the cluster purely by how much it warps the space around it and curves the light passing through. It's a completely independent scale, built on an entirely different principle from anything we've discussed so far. Astronomers call this gravitational lensing, because the bending mass acts like a giant, sloppy lens in space, distorting and magnifying and sometimes multiplying the images of whatever lies behind it. When the alignment is just right, the light from a single distant galaxy can be smeared into long curved arcs, or split into several copies, or in the most perfect cases bent into a complete glowing ring around the foreground cluster. A phenomenon so striking it's called an Einstein ring, a circle of distant light wrapped all the way around an invisible center of mass. These aren't simulations or artists' impressions. We photographed them. The great telescopes have captured cluster after cluster surrounded by these arcs and rings and ghostly multiplied images, the distorted faces of far more distant galaxies whose light got caught and bent on the long journey to us. And here is what those bent arcs tell us, again and again, with no reference whatsoever to how anything is moving. When astronomers measure the bending and calculate the mass required to produce it, they find, every time, far more mass than the visible galaxies in the cluster could possibly supply. The light is being bent as though the cluster were many times heavier than all its stars and glowing gas combined. The same missing mass that Zwicky found in the speeds of the galaxies, the same missing mass Rubin found in the spin of the spirals, shows up again, independently, in the precise way the cluster bends starlight from behind it. Three completely different methods. Three completely different principles. The same impossible answer. The universe is far heavier than it looks, and the extra weight gives off no light. You can perhaps feel the case tightening now. With one line of evidence, you can always hope for a mistake. With two, you grow uneasy. but when three utterly independent windows onto the universe, the motion of galaxies in clusters, the rotation of stars in spirals, and the bending of light across cosmic distances, all converge on the very same conclusion, the room for doubt starts to close. It becomes much harder to believe that we've made the same error 3 times in 3 different ways than to accept the thing all 3 are telling us. There is mass out there we cannot see, a great deal of it, and gravitational lensing was about to deliver something more than just confirmation. It was about to deliver what many scientists consider the single most convincing piece of evidence ever found, a kind of cosmic crime scene where the invisible mass was, for once, caught in the act of separating itself from the visible, leaving a clean and unmistakable fingerprint behind. To understand it, you need to imagine what happens when 2 enormous galaxy clusters slam into each other. This actually happens. Out in the depths of space, on timescales of hundreds of millions of years, whole clusters of galaxies drift toward one another under their mutual gravity and eventually collide, passing through each other in the slowest, grandest, most violent collision the universe has to offer. And there's one particular example, observed in detail, that has become legendary in this field. 2 galaxy clusters that had crashed through one another, leaving a wreckage we could study from a safe distance of billions of light-years. It's known as the Bullet Cluster, named for the shape of one of the gas clouds that got blasted by the impact. To understand why this collision matters so much, you have to understand that a galaxy cluster is really made of 3 different ingredients, and they behave very differently when 2 clusters collide. The first ingredient is the galaxies themselves, the stars. But here's the thing about stars in a collision. Space is so unimaginably empty that even when 2 clusters smash together, the individual stars almost never actually hit each other. The distances between stars are so vast compared to the size of stars that the 2 swarms of galaxies essentially pass right through one another, like 2 clouds of gnats flying through each other, hardly anything actually colliding. So the stars sail on through, barely slowed. The second ingredient is the gas. Between the galaxies in a cluster, there is an enormous amount of hot, thin gas. In fact, there's far more ordinary matter in this diffuse gas than there is in all the stars of all the galaxies combined. And gas behaves completely differently from stars in a collision. Gas clouds are continuous. They can't pass through each other. When the gas of one cluster meets the gas of the other, it slams together, compresses, heats up, drags, and slows down dramatically, like 2 splashes of water colliding rather than 2 clouds of gnats. So after the collision, the gas gets left behind in the middle, piled up and glowing in X-rays from the heat of the impact, while the galaxies sail on ahead, out past the stalled gas on either side. The gas lags, the galaxies lead. Now here's the crucial point. The gas is where most of the ordinary visible matter actually lives, much more than in the stars. So if dark matter were not real, if the missing mass were really just some form of ordinary matter we'd failed to account for, then the bulk of a cluster's mass should be sitting right there with the gas, piled up in the middle, slowed and heated by the collision. The center of mass should track the gas, because the gas is where most of the ordinary matter is. That's the prediction if there's no dark matter and we've simply miscounted the normal stuff. So the astronomers did the decisive experiment. They mapped where the gas was, using X-ray telescopes to see the hot glowing gas stalled in the center. And then, completely separately, they used gravitational lensing, the bending of light from galaxies far behind the collision, to map where the mass actually was. Where was the gravity? Where was the real weight of the system? If the mass tracked the gas, dark matter was in serious trouble. If the mass had sailed on through with the nearly collisionless galaxies, then there had to be some invisible substance that, like the stars, simply passed through the wreck without slowing. Something that doesn't interact with gas, doesn't pile up, doesn't heat, but only pulls with gravity. The answer was unambiguous. The mass, most of it, the great bulk of the gravity, was not with the gas in the middle. It had passed clean through, split into 2 clumps that had sailed on ahead with the galaxies, leaving the ordinary glowing gas stranded behind. The center of gravity and the center of the visible ordinary matter had physically separated, pulled apart by the collision and left in 2 different places. You could see it mapped out across the sky. Here is where almost all the ordinary matter is, the glowing gas in the center, and over here, offset separated, is where almost all the mass is, riding along with the galaxies that barely felt the crash. This is the cosmic crime scene I mentioned, and it's about as close to a smoking gun as this subject ever gets. The collision had taken a cluster and sorted it like a centrifuge, separating the dark from the visible and dropping them in different spots. The ordinary matter, the gas, got caught and stalled. The dark matter passed through almost untouched, betraying its presence only by its gravity, by the way it bent the light of galaxies far behind it. It's very hard to explain that separation with any theory that says the missing mass is just ordinary stuff hiding in the dark, because the ordinary stuff was right there in plain sight, glowing in X-rays, stuck in the middle while the gravity had walked off and stood somewhere else entirely. And notice what the bullet cluster quietly teaches us about the character of this stuff, beyond simply confirming that it exists. It tells us that dark matter is almost entirely antisocial. It passed through the collision, through the other cluster's dark matter, through the gas, through everything, almost without noticing, the way the transcript's image of an invisible glue would suggest, a glue that binds by gravity alone and refuses every other kind of contact. It doesn't crash. It doesn't compress. It doesn't heat up. It doesn't clump into knots or splash like the gas did. It barely even interacts with itself. It moved through one of the most violent events in the cosmos as though almost nothing were happening, registering its presence only through the gentle, patient, inescapable pull of its gravity. That non-reactiveness is one of the deepest clues we have about what dark matter might actually be. Hold it close because it's going to matter enormously when we finally ask the central question of the night. What is this stuff made of? Anything that can pass clean through an entire colliding galaxy cluster, through all that gas and all that other matter, without slowing down or heating up, has to be profoundly unlike the atoms that make up you and me and everything we've ever touched. We'll come back to that. Let's pull back now, all the way back to the largest scale there is, the structure of the entire universe, because dark matter's fingerprints are written there too, and on the grandest canvas imaginable. When astronomers made maps of where the galaxies are, spread across billions of light years, they expected, perhaps, a fairly even scattering, like sand sprinkled across a table. That is not what they found. Instead, the galaxies are arranged in a vast and intricate pattern, a structure so striking that it has earned a name of its own: the cosmic web. The galaxies aren't scattered randomly at all. They are strung together along immense filaments, bright threads of galaxies stretching across hundreds of millions of light years, and these filaments cross and tangle at great hubs where clusters of galaxies pile up, and between the threads there are enormous, nearly empty regions called voids, vast cosmic bubbles where there is almost nothing at all. If you could pull back far enough to take in the whole structure, it would look astonishingly like a network of neurons in a brain, or the threads of some colossal spiderweb, or the soap film between the bubbles in a sink full of suds. Bright matter gathered along the edges and the joints with great hollow emptinesses in between. And here is the question that turns this from a pretty picture into hard evidence. How did the universe come to be arranged this way? How did matter, starting out after the Big Bang spread almost perfectly smoothly and evenly through space, gather itself over billions of years into this delicate web of filaments and voids and clusters? The answer is gravity, working patiently over enormous spans of time. In the early universe, matter was very nearly evenly spread, but not perfectly. There were tiny ripples, faint regions that were a hair denser than their surroundings. And I want you to appreciate just how faint those ripples were, because it's one of the quietly astonishing numbers in all of science. The early universe was smooth to an almost unbelievable degree. The dense spots and the sparse spots differed from the average by only about 1 part in 100,000. Imagine the stillest pond you've ever seen at dawn, the surface so flat it looks like glass, and then imagine that the tallest ripple on that entire pond is finer than a hair. That's roughly how smooth the infant universe was, a vast, almost perfectly even sea of matter, with only the most delicate unevenness threaded through it, faint imperfections far too subtle for any eye to have noticed. And yet those almost imperceptible ripples were the seeds of everything. Every galaxy, every cluster, every filament of the great cosmic web, every star and world and living thing, all of it grew out of those whisper-faint variations, amplified over billions of years by the patient, relentless work of gravity. The grandest structures in existence began as the gentlest of imperfections in a nearly featureless sea. And gravity does a particular thing with even the slightest unevenness. It amplifies it. A region that starts out a little denser pulls in a little more matter, which makes it denser still, which lets it pull in more, and so on, a slow runaway that over billions of years turns faint ripples into the towering structures of the cosmic web. The dense seeds grow into filaments and clusters. The regions left behind empty out into voids. But here is the problem, and it's the same problem we keep running into, now writ across the whole sky. When scientists run this process forward in their computer simulations, when they take the early universe with its tiny ripples and let gravity sculpt it over billions of simulated years, and they include only the ordinary matter we can see, it doesn't work. There simply hasn't been enough time since the Big Bang for ordinary matter alone, with its relatively weak gravitational head start, to gather itself into the rich, fully formed cosmic web we actually observe. The structure that comes out of an ordinary matter-only simulation is too feeble, too sparse, too unformed. The real universe is more structured, more clustered, more web-like than ordinary matter alone could ever have built in the time available. The galaxies got organized faster and more thoroughly than the visible mass can explain. And then the scientists add dark matter to the simulation, and everything changes. Because dark matter, being far more abundant and feeling no pressure from light or heat to push back against its own collapse, could begin gathering into clumps very early, much earlier than ordinary matter could. While the ordinary matter in the young universe was still hot and turbulent and resisting collapse, the dark matter was already quietly pulling itself together into a scaffolding of dense regions and filaments. And then, once that invisible scaffolding was in place, the ordinary matter, the gas that would become stars and galaxies, fell into the gravitational wells the dark matter had already carved out. The dark matter laid down the framework first, in the dark, and the visible universe settled into it afterward, like frost forming along the threads of a spiderweb that was already there, tracing out a structure it did not itself create. When you run that simulation, early dark matter building the scaffolding, ordinary matter falling into it later, the cosmic web that emerges matches what we actually see in the sky to a stunning degree. The same filaments, the same clusters at the hubs, the same voids. The invisible scaffolding is the only thing that makes the timing and the structure come out right. The luminous cosmic web we map across billions of light years is, in a real sense, a portrait of the invisible one. The bright matter is simply decorating the contours of a dark structure that we cannot see directly but whose shape the galaxies faithfully trace. So that's another independent line of evidence, stacked on top of the others. And now we're ready to pay off the thread I asked you to hold, the comfortable hope that the missing mass might just be ordinary matter we'd undercounted. Because the deepest evidence of all comes from the very beginning of time, and it slams that door almost completely shut. Cast your mind back to the universe in its infancy, not millions of years after the Big Bang, but the first few minutes. In those first minutes, the entire universe was a furnace, so hot and dense that it acted like the core of a star, and in that furnace the lightest chemical elements were forged out of raw particles. This is one of the great triumphs of cosmology. Physicists can calculate with real precision exactly how much hydrogen, how much helium, and how much of a few other light elements should have been cooked up in those first few minutes. And crucially, the recipe depends very sensitively on exactly how much ordinary matter was present in that early furnace. More ordinary matter and the proportions of the elements come out one way, less ordinary matter and they come out differently. So by measuring how much hydrogen and helium actually exists in the universe today, we can run the recipe backward and calculate exactly how much ordinary matter there was at the beginning. We can count the atoms of the cosmos, and the answer that calculation gives is far, far too little. The total amount of ordinary matter, the protons and neutrons that make up every atom, every star, every cloud of gas, everything built from the elements, comes out to only a small fraction of the total mass the universe so clearly has to contain. The early universe recipe sets a hard ceiling on how much ordinary matter can possibly exist, and that ceiling sits far below what gravity demands. The missing mass cannot be ordinary matter that we simply failed to see, because the universe was never cooked with enough ordinary matter in it to begin with. There aren't enough atoms. There never were. Whatever the dark matter is, it is not made of the protons and neutrons that everything familiar is made of. It is something else, something that was not part of that early furnace's recipe at all. And then there's the final, most exquisite piece of evidence, the one I promised would close the door. It's the faint afterglow of the Big Bang itself. When the universe was very young, it was an opaque, glowing fog of hot plasma. And then, at a certain moment, as the universe expanded and cooled, it suddenly became transparent, and the light that was set free in that instant has been traveling outward ever since, stretched and cooled by the expansion of space until today it bathes the entire sky as a faint hiss of microwave radiation. We can detect it. It's all around us, coming from every direction. The oldest light there is, the literal first light of the cosmos, the afterglow of creation. We call it the cosmic microwave background. And when we map that ancient light with great precision, we find it is almost perfectly smooth, but not quite. There are incredibly faint patterns in it, slight variations in temperature from place to place across the sky, the imprint of those tiny ripples in the very young universe. And the exact pattern of those ripples, their sizes, their spacing, how loud the different patterns are relative to one another, depends in detail on what the universe was made of when that light was released. The early universe was, in effect, ringing like a bell, and the pattern of the ringing is frozen into that ancient light. By reading that pattern, cosmologists can weigh the universe's ingredients with extraordinary precision. They can measure how much ordinary matter there was, how much dark matter, and how much of the other strange ingredient we haven't even discussed tonight, the dark energy that drives the universe's expansion. And the answer that comes out of that ancient light agrees, beautifully and independently, with everything else. Ordinary matter, everything you've ever seen, every atom of every star and planet and person, comes out to only about 5% of the total contents of the universe. Dark matter comes out to around 27%, roughly 5 times as much as all the ordinary matter combined. And the rest, the largest slice of all, is that even more mysterious dark energy, a topic for another night. If you set aside dark energy and look only at the matter, only at the stuff that has mass and pulls with gravity, then the ordinary matter, the familiar stuff, is just about 15% of it. The other 85% is dark. That's the number the transcript named, and now you can see it isn't a guess or a fudge. It's the consistent verdict of the spinning of galaxies, the swarming of clusters, the bending of light, the weaving of the cosmic web, the forging of the elements in the first minutes, and the frozen ringing in the oldest light in existence. 6 independent windows. One answer. 85% of the matter in the universe is something we have never seen. Let that settle over you for a moment, in the quiet. Everything you have ever known, every face you've loved, every object you've held, every star you've ever wished on, the whole glittering inventory of the visible universe. All of it together is the thin 5%. You are made of the rare stuff. The ordinary, in the truest sense, is somewhere out there in the dark, and you have never once laid eyes on it, though it surrounds your galaxy, cradles it, and very likely drifts through your body gently and without consequence in this very moment. And before we ask what this stuff is, I want to linger on something the cosmic web quietly tells us, because it's perhaps the most personal fact in this entire story, and it's easy to walk right past it. If dark matter is what built the scaffolding of the universe early enough for galaxies to form, then dark matter is, in a very real and direct sense, the reason you exist at all. Follow the chain with me slowly, because each link is solid. Without dark matter's invisible scaffolding laid down in the young universe, the ordinary matter, the gas, would not have been able to gather itself into galaxies in the time available. We've seen that in the simulations. Ordinary matter alone, with its feeble gravitational head start, simply doesn't clump fast enough, and the universe you'd end up with would be a thin, formless haze of gas, drifting and unstructured, never quite pulling itself together. No galaxies, or at best pale, sparse, half-formed ones. And without galaxies, without those dense gravitational gathering places where gas can pile up and cool and compress, you don't get stars, because stars are born when great clouds of gas collapse under their own weight inside galaxies. And without stars, you don't get the heavier elements, because nearly every atom heavier than the lightest few was forged in the nuclear furnaces at the hearts of stars, or in the violent deaths of stars, and then scattered back out into space to be gathered into new generations of stars and worlds. The carbon in your cells, the oxygen you're breathing right now slowly as you settle towards sleep, the iron in your blood, the calcium in your bones. All of it was cooked inside stars that lived and died before the sun was born. And those stars only existed because galaxies existed to make them, and those galaxies only formed in time because dark matter built the scaffolding first. So when you trace your own existence all the way back, link by link, you arrive at the invisible. The atoms of you were assembled in stars, the stars were assembled in galaxies, and the galaxies were assembled in the gravitational wells of a substance that gives off no light and that no one has ever seen. You are, quite literally, a consequence of dark matter. The most intimate facts about you, that you have a body, that it's made of these particular elements, that there's a galaxy for you to live in and a star to warm you, all of it traces back to that quiet, unseen architecture. The thing we can't detect made the things we are. There's a strange tenderness in that, I think. The dark, which we so easily imagine as cold and empty and indifferent, turns out to be the thing that gathered the dust of the early universe into a place where, eventually, something could wake up and look around and ask what it all was made of. And here's a detail that makes the whole picture feel more vivid and more humble at the same time. You might imagine, given that there's 5 times more dark matter than ordinary matter, that the dark matter around you must be thick, dense, palpable, a heavy, invisible fog. But it isn't, not locally. Out here in our particular neighborhood of the galaxy, the dark matter is actually spread very thin. If you took a volume of space the size of your entire bedroom, the amount of dark matter inside it at any given moment would weigh almost nothing. Far less than a single grain of sand, a wisp so faint it barely registers. The reason dark matter matters so enormously is not that it's dense. It's that it's everywhere, filling the vast halos that stretch across distances so staggering that even a whisper-thin density, multiplied across all that volume, adds up to most of the mass in the cosmos. It's the same way that a thin haze, spread across a sky hundreds of miles wide, can add up to more water than a single heavy cloud. The dark matter near you is gossamer faint. The dark matter wrapped around the whole galaxy is overwhelming. Both things are true at once, and holding them together is part of learning to think on cosmic scales, that something can be almost nothing right here and almost everything when you pull back far enough. So now we arrive at the question we've been circling all night, the one at the very heart of the mystery. We know it's there. We've watched its gravity bend light and hold galaxies together and sculpt the entire structure of the cosmos. We know there's about 5 times more of it than all the ordinary matter combined. We know it doesn't shine, doesn't absorb light, doesn't reflect it, doesn't crash or compress or heat up, and barely interacts with anything except through gravity. We know an enormous amount about what it does. And yet, after all of that, there is one simple question we still cannot answer. What is it? What is dark matter actually made of? When you reach into it, if you could reach into it, what would you be touching? And the honest, humbling answer is that, despite nearly a century of work since Zwicky first noticed the problem, despite some of the most brilliant minds and most sensitive instruments humanity has ever built, we do not know. Not really. We have ideas, good ideas, carefully reasoned ideas, but every one of them is, for now, unconfirmed. The most abundant form of matter in the universe is a substance we cannot name. But let's walk through the best ideas because the reasoning behind them is lovely, and because understanding why scientists favor certain candidates tells you a great deal about the strange creature we're hunting. The leading idea for a long time has been that dark matter is made of some kind of particle. You're already made of particles, of course. Your body is a vast collection of protons, neutrons, and electrons arranged into atoms, arranged into molecules, arranged into you. The universe is full of particles, and physicists have cataloged them with exquisite care over the last century. So the natural thought is that dark matter is simply made of a kind of particle we haven't yet discovered. A new type of particle left over in enormous quantities from the early universe that happens to have mass, so it pulls with gravity, but that does not respond to light at all and barely responds to anything else. Think about what properties such a particle would need to have, because the requirements all flow directly from what we've already learned tonight. It would need to have mass so it can do its gravitational work. It would need to be electrically neutral, carrying no charge, because charged particles interact with light, and this stuff is utterly dark, so whatever it is, it must be blind to light and invisible to it in return. It would need to be stable, lasting for billions of years without decaying away, because it's still here, still doing its job, shaping galaxies that are as old as the universe nearly is. And it would need to be extremely reluctant to interact with ordinary matter or with itself by any means other than gravity. Recall the bullet cluster, where the dark matter sailed clean through the collision as though nothing were there. A particle like that, massive, neutral, stable, and almost perfectly aloof, would behave exactly like the dark matter we observe. For decades, the front-running candidate of this kind has gone by the name WIMP, which stands for Weakly Interacting Massive Particle. The name is almost a description of itself. Massive because it has substantial mass. Weakly interacting because the only force it feels besides gravity is the so-called weak force, one of the fundamental forces of nature, but one that, as the name suggests, operates only feebly and only at very short range. A WIMP would drift through ordinary matter almost as though the ordinary matter weren't there at all, only very, very rarely bumping into anything. And what made the WIMP especially appealing was a kind of beautiful coincidence that physicists noticed. If you take a particle with roughly the mass and interaction strength that certain well-motivated theories of particle physics predicted for entirely separate reasons, and you calculate how much of it would have been left over from the early universe, you get an amount that lands remarkably close to the amount of dark matter we actually observe. That near coincidence, the fact that a particle predicted for unrelated reasons would naturally show up in just about the right quantity to be the dark matter, was so suggestive that it earned its own nickname, the WIMP miracle. For a long time, many physicists were quietly confident that the WIMP was the answer, and that we'd catch one soon. So how do you catch a particle that drifts through ordinary matter almost without touching it? This is where the story becomes, to me, genuinely moving because of the sheer patience and ingenuity of the effort, and because of how it has turned out. The idea is this: even if a dark matter particle almost never interacts with ordinary matter, almost never is not the same as never. If dark matter is streaming through the Earth all the time, and it should be, since we're embedded in our galaxy's dark matter halo, and the Earth is plowing through that invisible sea as it orbits the Sun and as the Sun orbits the galaxy, then once in a great while, very rarely, a single dark matter particle should happen to strike the nucleus of a single ordinary atom and give it a tiny nudge, a faint recoil. If you could build a detector sensitive enough to register that minuscule, exceedingly rare nudge, you could catch dark matter directly. You could finally touch the thing. But the nudge would be so faint and so rare that any ordinary disturbance would completely drown it out. The patter of cosmic rays raining down from space, the faint natural radioactivity in the surrounding rock and in the materials of the detector itself, even a stray vibration, any of these would produce signals millions of times more often than a dark matter particle would. So to have any hope of hearing the whisper, you have to silence everything else. And the lengths to which physicists have gone to silence everything else are extraordinary. They build these detectors deep underground. Not in basements, deep underground, often a mile or more beneath the surface, in old mines and tunnels bored into mountains, using the entire thickness of the rock above as a shield to block out the constant rain of cosmic particles from space. They build the detectors out of the purest, least radioactive materials they can find, sometimes hunting for metals that have been shielded from cosmic rays for centuries, like lead recovered from ancient sunken ships that has sat quietly on the seafloor long enough for its own faint radioactivity to die down. At the heart of many of these experiments sits a great tank of liquid xenon, a heavy, ultra-pure noble gas, chilled and held in a vessel wrapped in layer upon layer of shielding, watched over by sensitive light detectors waiting in the dark. The whole apparatus is a cathedral of silence, built for one purpose: to be quiet enough that if a single dark matter particle ever brushes against a single xenon nucleus, the faint flash of that encounter might be seen. These experiments have names like Xenon and LUX and others, evolving over the years into ever larger, ever more sensitive incarnations, each one a marvel of engineering, each one representing the careers and hopes of hundreds of scientists. And for decades now, they have watched. They have sat in the deep silence of the rock, year after year, waiting for dark matter to knock. And here is the part of the story you should sit with, because it's the quiet, unresolved heart of the whole enterprise. They have not heard it. The detectors keep getting bigger and more sensitive, capable of registering ever fainter and rarer nudges, and the WIMPs have not appeared. The expected signal has not come. With each new, more sensitive experiment that reports nothing, the space where a WIMP could be hiding shrinks further. The WIMP miracle, so appealing for so long, has grown quieter and quieter as the years of silence have accumulated. The most natural, most favored candidate for dark matter has been hunted with magnificent patience and skill in the deepest, stillest laboratories on Earth, and it has refused to show itself. Now, I want to be careful about what that silence means because it's easy to misread it. It does not mean dark matter isn't real. The gravitational evidence we've spent all night building is overwhelming and untouched by any of this. Something is unquestionably out there bending light and holding galaxies together. What the silence means is narrower and subtler. It means that if dark matter is a particle, it is probably not the particular kind of particle we most expected it to be, or it interacts even more feebly than we hoped, hiding in a quieter corner than our detectors have yet reached. The silence is not a failure. The silence is data. Every year the detectors hear nothing. They teach us something real about what dark matter cannot be, and they push us to consider other ideas. This is what science actually looks like when it works on its hardest problems. Not a tidy march to an answer, but a long, patient narrowing, a steady ruling out of the comfortable possibilities, an honest willingness to keep listening to silence and let it reshape the question. And so, as the WIMP has grown quieter, other candidates have stepped forward, and they're worth meeting because they show how wide the possibilities still are. One of the most elegant is a hypothetical particle called the axion. The axion wasn't originally proposed to explain dark matter at all. It was invented to solve a completely different and rather technical puzzle in the physics of the strong nuclear force, a puzzle about why a certain kind of symmetry in nature is so precisely respected when nothing obviously requires it to be. To resolve that puzzle, physicists proposed a new particle, and when they worked out its properties, they realized something delightful. A particle with those properties, produced in the early universe, would be extraordinarily light, electrically neutral, exceedingly reluctant to interact, and present in vast quantities. In other words, it would behave just like dark matter. An axion would be far, far lighter than a WIMP, so light that catching one requires entirely different techniques, often involving strong magnetic fields and exquisitely tuned detectors that try to coax an axion into very rarely converting into a faint flicker of light. The hunt for axions is one of the most active frontiers in the field right now, and it carries that same quiet appeal the WIMP once had, a particle invented to fix one problem that turns out to fit another, deeper one almost for free. There are other candidates too. Some physicists explore the idea of sterile neutrinos, a heavier, shyer cousin of the ordinary neutrino, which is itself already a famously elusive, nearly massless particle that streams through the entire Earth without noticing it. A sterile neutrino would be even more aloof than its ordinary cousins, interacting through gravity and almost nothing else. Others wonder whether dark matter might come in more than one kind, a whole hidden family of particles with their own forces, a kind of shadow sector of physics running parallel to our own, touching our world only through the faint handshake of gravity. There's even a lingering, much-debated possibility that some of the missing mass could be locked up in primordial black holes formed not from collapsing stars but directly from the dense ripples of the very early universe, drifting dark and silent through the galaxy. Each of these ideas has its devoted advocates, its own clever detection strategies, its own reasons for hope. And so far, every one of them remains a candidate and not a conclusion. And if all of this, chasing a particle that may pass through a mile of solid rock without a flicker, building cathedrals of silence to listen for a knock that may never come, if all of it sounds like a fool's errand, like hunting for something that by its very nature refuses to be found, then I want to offer you a piece of reassurance from the history of physics itself. Because nature has played this exact game with us before and we won. There is a particle called the neutrino. It's an ordinary, confirmed, well-understood part of the universe now, but its story is worth telling tonight because it's almost a rehearsal for the dark matter hunt. Back in the early 20th century, physicists studying certain kinds of radioactive decay found that their books didn't balance. A tiny bit of energy kept going missing, vanishing from the ledger in a way that violated one of the most sacred rules in all of physics, the rule that energy can never simply disappear. It was a small discrepancy, but a real one, and it gnawed at them. And one physicist made a bold and almost desperate proposal. Perhaps the missing energy was being carried away by a new particle, one so faint, so reluctant to interact with anything, that it slipped out of every experiment completely unnoticed. A ghost particle, electrically neutral, nearly massless, almost impossible to detect. He proposed it and then half apologized for proposing it because he feared he had suggested something that could never, even in principle, be found. A particle that interacts so weakly that it seemed destined to remain forever hypothetical. Does that sound familiar? It should. It's the same shape of problem we've been living inside all night. A discrepancy in the books, resolved by proposing something we can't see. And for over 2 decades, the neutrino remained exactly that. A clever idea on paper, an unconfirmed ghost, accepted by many because it made the equations balance, but never actually caught. It seemed it might never be caught. Neutrinos, it turned out, are so aloof that trillions of them are streaming through your body every single second, pouring out of the sun, passing through the entire Earth as though it were a pane of glass, and they almost never touch anything at all. A neutrino could pass through a wall of solid lead light-years thick and have a good chance of coming out the other side untouched. How could you ever hope to detect something like that? And yet, eventually, we did. By building detectors of enormous size and exquisite sensitivity, and by being patient, by accepting that if a particle interacts only very rarely, then you simply need a great enough quantity of matter watched closely enough for long enough that, once in a while, you'll catch one of those rare interactions in the act. Decades after it was first proposed as a ghost that might never be found, the neutrino was directly detected, confirmed, made real. The thing that seemed impossible to catch was caught. And today neutrinos are not a mystery but a tool. We build great detectors to study them. We use them to peer into the heart of the sun and the depths of distant stars. We've turned the once undetectable ghost into a window on the universe. I tell you this because it's the great hopeful precedent hanging over the entire dark matter search. We have been here before. Nature has hidden something fundamental from us before, something that seemed by its very nature beyond our reach, and we found a way to reach it anyway, not through cleverness alone, but through patience, through scale, through the simple refusal to give up on something the equations insisted was real. The physicists watching their silent detectors a mile underground tonight are walking a path that has been walked successfully before. The silence they're listening to is the same kind of silence that once surrounded the neutrino, before we learned to hear it. None of this guarantees that dark matter will yield in the same way. It may be even shyer, even stranger, even harder to catch, or it may not be a particle at all. But the history says the impossible-seeming detection is not always impossible. Sometimes the ghost is real, and waiting, and catchable, if you're patient enough and humble enough to keep listening. But there is one more possibility, and it's the boldest of all, and it brings us right back to that unsettling thread I planted at the very beginning of tonight, the quiet suggestion that maybe we've misunderstood something more basic than we think. Because every idea we've discussed so far assumes that dark matter is a thing, a substance, some kind of unseen stuff filling the cosmos. But there's an entirely different way to read all this evidence, and it goes like this. What if there is no missing matter at all? What if the reason our calculations keep coming up short is not that the universe is full of invisible stuff, but that our law of gravity, the very rule we're using to do the calculation, is simply wrong on these enormous scales? This is a genuinely radical thought, so let's give it its due, because it's not the idea of cranks. It's a serious scientific proposal with serious people behind it. Remember how this whole mystery is built. Every single piece of evidence, the fast galaxies and clusters, the flat rotation curves, the bent light, the cosmic web, all of it, comes from the same basic move. We observe how things move or how light bends, we plug those observations into our equations for gravity, and we find that we need more mass than we can see to make the equations balance. We have always assumed that the equations are right and therefore the missing ingredient must be unseen mass. But there's another logical possibility. Maybe the visible mass is all the mass there is, and it's the equations themselves that need fixing. Maybe gravity, which we've only ever tested with real precision within our own solar system and its neighborhood, behaves a little differently out at the faint edges of galaxies, where the pull is extraordinarily weak. Maybe, in those gentle regions, gravity is just slightly stronger than our equations predict, and that extra strength, not any invisible matter, is what holds the fast outer stars in place. This idea has a name. It's usually called modified Newtonian dynamics, or MOND for short, and it was first proposed in the early 1980s by a physicist who noticed something striking. He found that if you tweak the law of gravity in one specific way, so that it gets a little stronger than expected only when the gravitational pull becomes very weak, then you can reproduce those flat rotation curves of galaxies beautifully without invoking any dark matter at all. And not just one or two galaxies. The modified law predicts the rotation of a remarkable range of galaxies with real success, sometimes more cleanly and with fewer adjustable knobs than the dark matter explanation requires for those same galaxies. That's not nothing. That's a genuine, uncomfortable success that the idea's defenders rightly point to, and it's the reason the proposal has never simply gone away. At the scale of individual galaxies, this rival idea does some things impressively well. So why isn't this the accepted answer? Why do most physicists still favor invisible matter over modified gravity? The honest reason is that, as elegant as the modified gravity idea is for single galaxies, it has a much harder time with everything else. It struggles to explain the swarming galaxy clusters that started this whole story with Zwicky. It struggles to explain the detailed pattern frozen into the cosmic microwave background, that ancient ringing of the early universe, which the dark matter picture fits with stunning precision. And perhaps most tellingly, it struggles mightily with the bullet cluster, that cosmic crime scene where the mass and the visible matter were physically pulled apart and left in different places. If there's no dark matter and gravity simply works differently, then the gravity should still be centered on where the matter actually is, on the glowing gas in the middle. But it wasn't. The gravity had walked off and stood somewhere else, separated from the visible stuff. That separation is very natural if there's an invisible substance that sailed through the collision, and very awkward to explain if all you have is a modified law of gravity acting on the matter you can see. The bullet cluster is, for many scientists, the observation that tips the balance decisively toward real, physical, invisible matter. So where does that leave us? It leaves us, beautifully and honestly, without a final answer. The overwhelming majority view, supported by the widest range of evidence, is that dark matter is a real substance, most likely some kind of particle we haven't yet identified, woven through every galaxy and cluster, sculpting the cosmos with its gravity. But the alternative, that we've misunderstood gravity itself in the faint reaches of space, has not been entirely ruled out, and a minority of thoughtful scientists keep it alive, keep testing it, keep pushing on the places where the standard picture is least comfortable. Both camps agree completely on the observations. The galaxies really do spin too fast. The light really does bend too much. The web really is too structured. The disagreement is only about what those facts are telling us, that the universe is full of unseen stuff, or that our deepest law of motion has a hidden flaw. And the truth is, we don't yet know which. Either answer, if confirmed, would reshape physics. One would reveal a vast new kind of matter making up most of the universe. The other would overturn our understanding of gravity, a thing we thought we'd nailed down centuries ago. There's a strange thrill in that the most ordinary seeming questions about why stars stay in their galaxies lead straight to the edge of what we understand, and that even now the edge is genuinely open. I find something deeply reassuring in this state of not knowing, and I want to try to share why, because it's easy to hear all of this as a kind of failure, a century of work, and we still can't say what most of the universe is made of. But that's not how it feels from the inside, and I don't think it's how you should carry it as you drift off. Consider what we have actually accomplished. Starting from nothing more than the careful observation that some stars were moving a little too fast, human beings have established, beyond reasonable doubt, that the universe is overwhelmingly composed of something profoundly unlike anything we have ever touched. We have measured how much of it there is to within a few percent. We have mapped where it sits around galaxies and across the cosmic web. We have caught it separating from ordinary matter in a collision billions of light years away. We have built cathedrals of silence a mile underground to listen for it. We have done all of this for a substance no one has ever seen. That is not a failure. That is one of the most extraordinary acts of collective reasoning our species has ever performed, to chart in such detail the contours of the invisible, guided only by the faint and patient testimony of gravity. And the not knowing at the center of it is not an embarrassment. It's an invitation. It means the universe still has its largest secret in reserve, still folded up and waiting, and that somewhere right now there are people in those deep laboratories, watching their detectors in the dark, and people at their telescopes mapping the bending of ancient light, any one of whom might, on some ordinary morning, see the signal that finally tells us what 85% of the matter in the universe truly is. That discovery hasn't happened yet. It's still out there in front of us. We're living in the long, patient middle of the story, in the chapter before the reveal, and there's a particular kind of privilege in that, to be alive while the question is still open, still genuinely mysterious, still ours to wonder about. So let's draw all of this back down now, gently, from the scale of the whole cosmos to the scale of you, lying wherever you are, listening in the quiet. You live inside a galaxy. It's easy to forget that, because from down here on the surface of one small planet, the galaxy doesn't feel like a place we're inside. It feels like something else out there that we look at. But the Milky Way is not a thing in the distance. It's our home, and we are deep within it, about halfway out from the center, riding along one of its spiral arms. And everything we've learned tonight applies to it as much as to Andromeda or to Zwicky's distant cluster. Our galaxy, too, spins too fast at its edges to hold itself together on the strength of its visible stars alone. Our galaxy, too, must be cradled in an enormous halo of dark matter, a vast, roughly spherical cloud of the invisible stuff, far larger than the bright disk of stars we picture when we imagine the Milky Way, extending out and out into the dark in every direction, dwarfing the glowing part it surrounds. The familiar spiral of stars is just the luminous sediment that settled into the center of that great dark sphere. The real Milky Way, the full extent of it, is mostly invisible, and it reaches out around us much farther than any star. And you are not sitting still inside it. Nothing here is sitting still. The Earth is turning, and it's circling the Sun at enormous speed, and the Sun, carrying the whole solar system with it, is sweeping in a great slow orbit around the center of the galaxy, moving at something like 500,000 miles an hour, taking a couple of 100 million years to complete a single lap. The last time the Sun was in the part of the galaxy it occupies tonight, there were no human beings, and dinosaurs had not yet appeared. That's how slow and grand the turning is. And as the Sun carries us along on that immense circuit, it is moving through the galaxy's dark matter halo, plowing steadily through that invisible sea, the way a swimmer moves through water, the way a traveler moves through still night air, which means that from our moving point of view, there is, in a sense, a wind. Not a wind of air, but a wind of dark matter. A steady stream of those unseen particles, whatever they are, flowing past us and through us as we ride the Sun through the halo. It blows from the direction we're heading, the way rain seems to come at your windshield from ahead when you drive through a downpour on a still night. Physicists even use this idea in their searches, because the Earth's own orbit around the Sun slightly speeds us up and slows us down against this dark matter wind over the course of a year. They look for a faint seasonal rhythm in their detectors, a signal that would rise and fall with the seasons as we tack into and out of the breeze. The wind is gentle beyond imagining, so gentle that it passes through the entire bulk of the Earth without noticing it's there. But it is, in principle, blowing past you right now, and has been blowing past every living thing on this planet for as long as there has been life here. Sit with that softly in the dark. As you lie there, perfectly still, feeling held by your bed and the quiet of the room, you are in fact hurtling through the galaxy at 500,000 miles an hour, and an invisible river of the universe's most abundant matter is streaming silently through the room, through the walls, through the blankets, through your body, through the very atoms of you. Trillions upon trillions of dark matter particles are very likely passing through you in the time it takes to read this sentence, and not one of them touches you in any way you could ever feel. They don't push you, don't warm you, don't disturb a single atom. They pass through the solid Earth as easily as light passes through glass, through the planet and out the other side, on their long way around the galaxy, indifferent to your existence and yet, on the largest scales, responsible for the very shape of the home you live in. You are, at this moment, swimming in the great dark ocean of the cosmos, and you cannot feel the water at all. There is something in that fact that I find quietly steadying rather than frightening, and I hope you feel it that way too as you drift, because it gently dissolves an old and lonely picture of the universe, the picture of cold, empty space, of little islands of light marooned in an endless black nothing. That picture was always partly a trick of our eyes, which can only see the candle flames and never the house. The truth is fuller and warmer than that. Space is not mostly empty. It is mostly full of a quiet, dependable presence that holds everything together, that gathered the matter into galaxies in the first place, that laid down the scaffolding our own Milky Way settled into, that has been faithfully cradling the stars for billions of years without ever once asking to be seen. We evolved on a small bright planet to notice the things that glow, and so we mistook the glow for the whole. But the dark was never the absence of the universe. The dark was most of it. And there's a deeper lesson folded into all of this, one worth carrying with you beyond tonight. Dark matter is the universe's gentle reminder that our senses were never built to perceive the truth of things. They were built for something far more local and immediate, for finding food, avoiding danger, recognizing a face across a fire, surviving a single lifetime on the surface of one world. Our eyes catch a thin slice of light. Our hands feel only the matter that resists them. And for the everyday business of being alive, that's plenty. But the cosmos was never under any obligation to limit itself to what a creature like us happens to be able to detect. And it didn't. Most of what exists slips entirely through the net of our senses, the way the dark matter wind slips through your body. Present, real, consequential, and utterly invisible to the instruments evolution gave us. To know that, and to keep going anyway, to keep reasoning our way toward the parts of reality we'll never directly touch, is one of the quietly heroic things about being human. Think back, now, to the very beginning of this story, to the difficult man at his telescope in the 1930s, insisting that the numbers didn't add up, that the universe weighed more than it looked, and being ignored for the better part of 40 years. Fritz Zwicky did not live to see the full vindication of what he had glimpsed. He didn't get to watch the rotation curves come in flat, didn't see the light bend in the great clusters, didn't see the bullet cluster split its dark from its light, didn't see the ancient afterglow of the Big Bang confirm his missing mass to within a few percent. He simply saw the truth before the world was ready, and held to it, and was mostly disregarded for it. And then there was Vera Rubin, who chose the quiet, unfashionable problem precisely because no one would crowd her out of it, and who, through sheer careful patience, gathered the evidence that finally made the world pay attention, and who, it's worth saying, was never awarded the Nobel Prize that many felt her work deserved. The history of this idea is, in the end, a very human history. It's a story of people noticing what others overlooked, of being patient with measurements everyone else thought were settled, of trusting the data even when the data was deeply inconvenient, and of being willing to say out loud that most of the universe is something we cannot see. That takes a particular kind of courage, the courage to follow the evidence into the dark and report honestly what you find there, even when what you find is mostly a question. So this is where we'll let the night settle. We came in tonight with a simple, almost childlike question: what is dark matter really? And we followed it as far as the answer goes, which is to the honest edge of human knowledge. We found that most of the universe is invisible, and we found the overwhelming evidence that it's truly there, written in the spin of galaxies and the bending of light and the oldest glow in the sky. And we found, at the very center, a mystery still genuinely unsolved, a question still waiting for whoever, someday, will finally see what the rest of us never could. There's no neat bow to tie on it, and I think that's exactly right. Some of the best things to fall asleep to are the questions that are still open. When you look up at the night sky tomorrow or some clear evening soon, I hope you'll see it a little differently. Those scattered points of light will still be there, beautiful as ever. But now you know they aren't the universe. They're the candles in the great dark house. They're the bright sediment settled into something vast and unseen. And the blackness between them, which you spent your whole life reading as emptiness, is the one place where most of everything actually is: quiet, patient, holding it all together, flowing this very moment through the room where you're resting, through the walls and the blankets and the still atoms of you, on its long way around the galaxy. You don't have to solve it. You don't have to understand every step of the reasoning, or remember the names, or hold the numbers. It's enough, tonight, simply to know that the universe is fuller than it looks, that the dark is not empty, that you are swimming in an invisible ocean that has been gently holding the stars in place since long before the first living thing opened its eyes to wonder about any of it. There's nothing to do with that knowledge but rest inside it. The dark is not against you. It never was. It's the larger part of the home you've always lived in. So let your thoughts grow slow and soft now. Let the galaxies turn somewhere far above you, held in the arms of something we still don't have a name for. Let the quiet ocean stream through the room, unfelt and harmless and immense. There's nothing you need to figure out before morning. The universe has kept its biggest secret for billions of years, and it will keep it a little longer patiently while you sleep. Rest easy. The stars will hold. Good night.